Okay, yesterday we had a look at the whole idea of the blackbody radiation. And just to recap as to what is the ultraviolet catastrophe, we find that when we do a radiation intensity curve, where intensity is measured in terms of brightness on the vertical axis, and wavelength, or lambda in meters, is on the horizontal axis, we get a specific characteristic shape. And the shape is a long tapering tail towards the longer wavelengths. This is the radio end down here. And up at the ultraviolet end, up here, we have a rapid drop-off at the UV end. In fact, we find that we don't have much, even if we heat it up really, really hot, we don't get much X-ray. In fact, whether or not they're really classified as X-rays is debatable. We just have high UV. We don't get any X and gamma ray really by heating it up. Now, why was this a catastrophe? Because this is the experimental data. This is experimental. Now, the experiment can't be, the actual, what we observe can't be an error because it is actually what is real, it's what's true. But what the catastrophe was is that the Maxwell's equation, James Clerk Maxwell, who put all this together, gave us all the equations which defined and described the wave property of light, said that the shape should look like that. And we got that the bottom part of the curve that's in the radio end, this section here, agreed with Maxwell's equations, but there was a deviation of what went wrong up here and to the experimental data. And this was on the UV end, and we called this ultraviolet catastrophe, as if a catastrophe was actually going to happen. But it was a big problem.
Was it a catastrophe because they weren't matching, or a catastrophe because the people went up there would have been?
Well, I don't exactly know. That's a good question. Was the word catastrophe meaning as in it's such a disaster because this would mean that we're breaking the laws of conservation of energy, or should it be going because it just doesn't match? Yeah, I don't know. That's what it is called. I'll have to go back in time and find out and change history. Okay, I'll go back and tell them the answer and I'll be famous. Okay, rightio. So this was the problem. Remember, and there's a big push in the study that you have to be able to apply the observations and the ideas of science to all of this stuff. And we know that we observe in scientific method, we observe something and then we come up with a hypothesis and we test it, and if it's true, then it goes as part, it is accepted as part of the theory, isn't it? If it's not, we have to go back and re-hypothesize. So we can constantly update our theory to hone it and make sure that it is reflecting the reality that we see. So this is a good time to have a look at, what happens to scientific theory when part of it doesn't work. So we've got to come up with something which will explain away this result. And remember, as scientists, are we quite willing to simply reject the whole thing and just start all over again? Yes, we are. And science is great at doing that. We rejected geocentrism when we discovered that we were actually orbiting around the sun. We threw away that and another theory came in, and so on. So we are quite happy to throw things out, and we're also happy to modify. In this case, it's just a modification to the theory. So how do we explain this deviation over here? It took a man by the name of Max Planck. So his name is Max Planck. And he's a German physicist. He's quite old at this stage compared to Einstein. and it's happening back in the early 1900s, or late 1800s, that this is happening. I'll just make sure I've got the right date for this. I haven't got the Australia in front of me. Sorry? 1930, is it? Yes, just before that, actually. Yeah, it's around that time, early 1900s. Max Planck is going to come up with a solution to this problem. And he does it in a very unique and novel way that Einstein is then going to grab hold of and modify our entire physics further. So Max Planck is one of the reasons why Einstein is so famous. Okay. So let's go through and see what is his solution to all this problem. Okay. Nope, not that one. Okay. Rightio, this is the answer to the book in the red book, the sheet on the red book on page 20. So this is a pictorial representation of Max Planck, and here's Max over here, thinking and writing. Okay. Now, what we see over here is the ultraviolet catastrophe, and I've got a diagram. I'll just make this slightly bigger so you can see it. And that diagram represents the ultraviolet catastrophe. So you should be able to write it down and so on. Okay? I think I've already got that in your book, is that right? Okay. So we start at the ultraviolet catastrophe. So, what was his grand idea? Now remember, the idea is just simply a hypothesis and then testing. So remember this, at this stage, it's hypothesis. So he's going to hypothesize that electromagnetic radiation emitted from a black body is not continuous. It's grainy, it's granular, it's sandy. Okay? It's not continuous. In other words, we would, in the modern day, call it digital. Okay? It's not continuous, but it's emitted in packets or bundles. And these bundles are going to be called quanta, from the Latin meaning amount. Okay? So he's going to say, okay, rightio. We are so used to thinking of an electromagnetic wave as a wave. Let's try and think of it not as a wave, but slightly as a particle. Okay? And this particle or packet of energy is going to be called a quanta. Okay? And just so that we do know our Latin, the word quanta and quantum, and you've heard of quantum, as in quantum mechanics before. Quanta is the plural, as in amounts. Quantum is an amount. Okay. And he's going to say that each quantum has a specific energy level defined by its frequency. So we need to know its frequency only. So high frequency particles have high energy. Okay? So each quantum has a specific amount of energy, and that energy is dependent upon only how fast it vibrates. Okay? And the radical part of all of his idea is it's going to come down to, he's going to give an equation. Okay? He doesn't actually give an equation. We found the equation later. The equation is going to be E equals hf. But what he's going to say is the energy of the quantum is proportional to the frequency, directly proportional. We're going to find later, now we know in maths that if we want to get rid of this proportionality sign and make it an equality sign, what do? We make it equals and put a constant in, don't we? Yes. So we get E equals Kf. Okay? Now this K there, in English-speaking countries, we often put a K in. Okay, K is the great constant of proportionality, and the other one that we use at times is C. But he's German, and in Germany, the most common letter at the time was not a K, but an H. The H of the constant of proportionality was H. Okay, so that's the reason why it becomes E equals HF. Now, so he's very, very humble man. He's not going to call this constant after him, but we do. It's called Planck's constant. And it was found later on, not by him, but it was, well, actually it was by him, but it was confirmed later on by other scientists as well. And we now know the value, and Planck's constant is 6.626. 6.626 by 10 to the negative 34. And heaven helps me, I can remember the units of it. Okay, so that's that number. Look at the size of it. It's tiny. The reason being is this is the amount of energy a single quantum of light contains. Now we all know that the name of the quantum of light will change very soon by Einstein, and the name that Einstein's going to give it, if I can just get this right, this value, is the quantum. It's not too big. Slow it down. Is going to be changed to the word photon. Okay? And we've already used this formula before. We used it earlier last year to work these out. So we know that H is a very, very small number because the photon carries only a very small amount of energy. But we get a lot of them together and they get a lot more energy. Okay? So remember at this stage, we specifically have only got no proof of this. He's just saying that E is proportional. I'll just get my thing up firstly. We're going to say E is proportional to frequency, and therefore E would equal H times F. That's all he's saying. So he's not actually producing an equation which is usable at this point. Okay, he's just saying it's proportional. Okay, any questions so far on this? Come on, machine. Okay. It's not going down. Oh, okay, rightio. Now, he agrees with us with the kinetic theory of matter. Now, remember yesterday we talked about the kinetic theory of matter, and we said that the reason why atoms emit radio waves and microwaves and so on is that charged particles oscillate backwards and forwards. So according to the kinetic theory of matter, as electrons and also atoms vibrate backwards and forwards in their lattice or in their solid, they will emit radio waves and microwaves. We mentioned that yesterday. Are we okay with that? Okay. Now, there is what we call harmony. And if people here have any idea of music, we all know that when we sing, we don't all sing the same note, do we? Okay. So I'm just going to take a few moments I'll let you just copy down that before I go any further. So I'll just pause here and let you copy that. Okay. So this we just finished off with at low temperatures. The vibration is by the entire atom as well as the electron, and therefore we have different types of frequencies. We've got resonance, we've got clapping half as fast, and so on. Okay. Now, as we start to heat up, we get something happening. At the radio end, atoms can still vibrate, and they vibrate quite easily backwards and forwards. Some are vibrating slowly, some are vibrating faster, and so on. So as we go further and further up, at this end here, all of my atoms are vibrating reasonably slowly, and so are their electrons. Then as we heat up, the atoms here are vibrating maybe at half speed or even double that speed, but most of the atoms are vibrating at this frequency backwards and forwards. And so are their electrons. So the most common the most common wave that is being emitted at this time is of this wavelength just here. Okay? The problem is the energy needed to move an atom forward and backward in its vibration for a UV wave is too large. So the energy needed for an atom or an electron at this stage to vibrate backwards and forwards because of the temperature is just too much. And that means we get a collapse in the UV end. And it drops rapidly down to zero. Okay? So remember, at the peak wavelength, most of the vibrations and most of the parts of the atom or the electrons are all emitting this wave because they're all in sync with each other, they're in harmony with each other. Exactly. They're vibrating together. But there is just too much energy required for them to vibrate and to liberate UV. Are we okay with that? And that was the idea that Planck comes up with. That the reason why the radio waves, the microwave, the infrared waves are actually being, and the light waves, are being emitted is because particles are oscillating according to kinetic theory. But these particles have a maximum kinetic barrier that they have to go through because they have, what word? Inertia. The inertia is required to accelerate and decelerate, move it backwards and forwards. Remember, these are oscillating particles. They're going forward, then back, forward, then back. That massive deceleration required is just too much energy needed. Okay? So,
What does it say on the left is the one?
oh, that's a move over there? Okay. So, as the temperature increases, there is enough energy for the atom to vibrate at the higher frequencies, thus visible light. So if we start by heating an object up, this is what this is saying, this one up here, is saying that at lower temperature, the whole atom moves backwards and forward, it emits radio waves. If you heat it up, it starts to emit microwaves. Then eventually infrared, and then if there's enough energy, we'll start to see the higher frequencies, which is light and the first part of UV. But the problem is there enough energy eventually to get heated up, even hotter, will it start getting gamma rays and X-rays? No, there is not enough energy in the heating process to be able to do that happen. Is that making sense? Okay. And there's a second thought bubble over here which says, though the energy required to produce visible light frequency is present, remember some atoms vibrate in front of that, higher frequencies, and some give us lower. That gives us this characteristic shape. Okay? Remember, they're all vibrating at different speeds, but there is the most likely speed, and that's formed by the peak wavelength. Okay. Any questions so far on this? Okay. I'll just pause it. Yeah, I'll pause it. And finally, remember it's a big spiral. According to the diagram, it's spiraling in. The energy required to make an atom vibrate at frequencies higher than visible light, in other words, UV, the amount of the acceleration and deceleration required for this to happen with the atom and the electrons is too high. It can't be supplied from heating alone. So we can't get anything higher than the first part of UV and maybe the end of UV, and maybe we could call it the lower part of X-rays. So to make an atom vibrate, the frequency is high enough to emit radiation at UV is too high. So it starts to rapidly drop off in the UV end. Now, what does this mean about Maxwell's equation? Well, Maxwell's equation is assuming that the emitter, that's the atom, is so small that it doesn't have inertia. And that's the reason why the equations for Maxwell weren't working in the UV end. But they were working okay in the radio end. Is that making sense to everyone? I'll ask that question again. So Maxwell, when he realised that the inertia of the atom in the UVN did have an effect, then took that into account with his understanding, and the equations were just corrected and fixed up. So therefore the experimental data, which was this shape that we are used to, this shape here, matches now with the Maxwellian equations. Okay. So it wasn't a major mistake that Maxwell had made, it was quite minor, but it was a great, because that minor mistake was made, a great leap forward in our understanding of electromagnetic waves came. And we call this solution as Planck's solution to the Blackbody radiation problem. Okay. And as a result, we now know a lot more about our about photons, which is what the quantum will become, and we also know about how photons as particles and as waves interact with each other. Okay, we'll call it there. Right, this is the page from your notebook, and it says to calculate the missing values of each. Now you're going to be using E equals HF, and we know we've used this formula before. And at the same time, we're going to be using C equals F lambda. Remember, C equals F lambda, so we change the pen. C equals F lambda is a version of the universal wave equation. The universal wave equation says the velocity of any wave is equal to the frequency times its wavelength. But for a electromagnetic wave, what is the speed of the wave?
Speed of light.
Speed of light. So this is the speed of light wave equation. Okay. So to find, if we've got a frequency, here's the frequency number A. To find the wavelength, then we will use this equation here, C equals F lambda. So we have 3 by 10 to the 8th equals frequency 2.0 by 10 to the 15 times the wavelength, and rearranging that we get the wavelength in metres as, can I have a value please?
150 times 10 to the negative 9.
150 times 10 to the negative 9 metres. Okay, and remember negative 9 is another way of saying nano, so we are used to 150 nanometres. This is actually just below one of the colours like red. Okay. Right, now we've worked out how to use that equation. We're going to use to find the energy equation. The energy is equal to HF, so E equals H is 6.26, 626 I should say, undo 626 by 10 to the minus 34 times the frequency, which is 2 by 10 to the 15. Can I get the answer to that one? So what was it? 1.32. Yep.
Times 10 to the negative 18.
Negative 18. Okay. Keep that number, please, on your calculator, please. Okay. And that's in joules. Now, joules is that's the unit that we use for all energy, but we have another unit of convenience called the electron volt. And I introduced you to this last time. That's the amount of energy required to accelerate an electron through 1 volt. But it's a convenient measure of energy. To convert between joules and energy, of electron volt, joules to electron volts, we divide by 1.6 by 10 to the minus 19, which we recognise as the charge on the electron. So we had a few moments ago, what was this value here? Please just clean it off.
1.32 times 10 to the negative 18.
Good, 10 to the negative 18. If you divide that number by 1.6 by 10 to the minus 19, you'll get it in electron volts, which hopefully is a much more convenient number. 8.3 electron volts, good. So just to remind ourselves how that works as a loop table, joules to electron volts you divide by 1.6 by 10 to the minus 19. And to go the other way, what would we? Times by 1.6 by 10 to the minus 19. Okay, your homework will be to complete that sheet, that question off there, and get your book, the record ready and up to date to that point, as well as complete your assignments. Okay, thank you very much, ladies. Off you go.